Morning everyone, this is Mohit from CSCD section, and today my physics topic of concept video is on high magnetic field superconductors. So we're going to see its introduction, what are the types of superconductors, how they affect, what are the factors, and what are the costs, how are their impact in social and environmental. Okay, now first the introduction to superconductivity. So superconductivity is a phenomenon or it's a mechanism where a material exhibits zero electrical resistance and expulsion of magnetic fields when the temperatures decrease below a certain critical temperature known as PC. Now, this means that when the material becomes superconductive, it can conduct electricity without any energy loss due to resistance. Next, the zero electrical resistance, where the superconductors allow electrical current to flow without any loss of energy. This is a contrast to regular conductors where energy is lost due to as heat due to resistance. Now, we know the Mainzel's effect, where the superconductors exhibit perfect diamagnetism, meaning they have an expel magnetic fields from within themselves where they transition into the superconducting state. This is known as the Mainzel effect. So, as a result, a superconductor will levitate a magnet due to expulsion of magnetic fields from the superconductors. Next, the critical temperature TC we say, the temperature below which a material becomes superconductive is known as a critical temperature or TC. Above this temperature, the material behaves like a normal conductor. At the time of critical temperature, the conductor becomes like a superconductor. Next, the high temperature superconductors, we say HTS, have a higher TC or the critical temperature compared to normal conventional superconductors. Next, with the types of constructors, we say the two types. Type 1 constructor superconductors and type 2 superconductors. So type 1 superconductors are the materials that exhibit superconductivity at low magnetic fields and temperatures. They completely expel magnetic fields or the Mainzer effect and transition abruptly to a normal state once a critical magnetic field is reached. Next, we have the type 2 superconductors. These materials are more suitable for high magnetic field applications. They allow some magnetic fields to penetrate in a mixed state, making them more robust in high field environments. Type 2 superconductors are typically used in applications such as MRI and particle accelerators. Next, the high magnetic field superconductors are materials that can maintain superconductivity in presence of strong magnetic fields. These superconductors are specifically designed to function high field environments where typical superconductors might lose their superconducting properties. Next, the importance. What is its importance in various scientific and industrial fields? So due to high magnetic field superconductors are crucial in technologies that require the generation of strong magnetic fields without any energy loss. These include applications like particle accelerators, we say MRI machines, and magnetic levitation. The ability to operate in high magnetic fields make them indispensable in areas such as first is medical imaging. So MRI, we know as the machine resource imaging, or this is magnetic resonance imaging. Machines uses high magnetic field superconductors to generate stronger magnetic fields for imaging the human body. It is more advanced to the X-ray machine. Next, we have the particle accelerators. Particle accelerators where superconducting magnets are used in particle accelerators like CERN or Large Hadron Collider (LHC). We say to accelerate particles to high speeds. Energy transmission where superconducting power cables can carry electricity without any energy loss and an efficient means of power distribution. Next, the role in generating high magnetic fields. So superconductors in high magnetic and field environments can support the creation of extremely strong magnetic fields. So in many cases, we see the strength of magnetic field produced which is directly proportional to the superconducting material's ability to withstand magnetic forces without breaking them out into a superconducting state. Now, these high magnetic field superconductors are used in powerful magnets for various scientific devices, including those in fusion reactors, research labs, and more. So, characteristics of high magnetic field superconductors. So, characteristics critical magnetic field. So, the HC we say critical temperature is TC and critical magnetic field we say is HC. So, every superconductor has a critical magnetic field beyond which it loses its superconductivity and becomes a normal conductor. So the high magnetic field superconductors are engineered to have a higher critical magnetic fields, allowing them to operate in environments where typical superconductors would fail. The type 2 semiconductors for high fields. Let us say type 2 semiconductors are essentially important for high magnetic field applications. So unlike like type 1 semiconductors, type 2 materials allow magnetic fields to partially penetrate to them, forming what is known as a vortex state. So this makes type 2 semiconductors, superconductors, more suitable for environments with high magnetic fields. These superconductors exhibit a superconducting normal mixed state, or called as the vortex state, that is stable in high magnetic fields, making them more resilient to disruptions. So the type 2, so the type 1 superconductors characteristics were the pure superconductors that exhibit superconductivity at very low temperature. They show a complete expulsion of magnetic fields, which is known as the Mincer effect, we know. Next, the critical magnetic field Hc, where it can withstand a weak magnetic field before they transition to normal conducting state. And we have the transition to normal state we said earlier, with superconducting normal conducting state in time what materials is abrupt. There is no intermediate state. So the examples of type 1 superconductors are lead, mercury, tin, and aluminium. Now, this is type 2 semiconductor characteristics have more complex response to magnetic fields compared to type 1. Next, they can withstand much higher magnetic fields and remain superconducting even when external magnetic fields are much stronger than the critical field of type 1 materials. So there are two critical fields, He1 and He2. So the He1 is lower critical field and He2 is upper critical field. So is lower critical field below this field. The type 2 superconductors exhibit perfect diamagnetism, expelling all magnetic fields like type 1 superconductors, and which is the upper critical field, which is Hc2. Once the electrical magnetic field exceeds Hc2, the superconductor transitions from the superconducting state to the normal state. So they change. So between Hc1 and Hc2, a mixed state occurs where magnetic flux penetrates the superconducting form of vortices, or we say vortex state. Now, the examples of type 2 superconductors are niobium titanium, niobium tin, yttrium barium copper oxide, and bismuth strontium calcium copper oxide. We say BSCCO. This is YBCO is yttrium barium copper oxide, which is a high temperature superconductor. Niobium tin, NB3 actually, it's NB3SN, and niobium titanium NBTI, and bismuth strontium. Okay, we know that. Next is the mechanism between. Now we have all learned the characteristics. Now let's see what is the mechanism behind this high magnetic field superconductivity. So first is the copper pair mechanism, where a superconductivity arises from the formation of copper pairs where electrons pair up and move through material without resistance because of the conductors. Next, these paired electrons move in a correlated manner, forming a condensate that behaves collectively rather than individually in the form of superconductor. Next, the critical magnetic field and temperature. Each superconductor has one TC, or like not one the value. It has two factors. One is the critical magnetic field Hc and critical temperature Tc. So the critical temperature Tc is the temperature below a material becomes superconductor. And critical magnetic field, the strength of magnetic field beyond which superconductivity is destroyed. Next is the high magnetic field effects. As the magnetic field increases, it can disrupt the superconducting state. However, the magnetic field superconductors like type 2, we say high ones, remain superconducting in presence of strong fields due to the vortex state or vortex formation. Now in flux spinning, we see the high magnetic field superconductors, flux spinning occurs, where defects in the material trap the vortices, preventing them from superconducting state even in high magnetic field. So this is crucial for applications. It's very important for applications where strong magnetic fields are required, like as flux spinning helps maintain stability and reduce energy losses. So challenges in high magnetic field superconductors, where first thing is the critical temperature and magnetic field limitation. So every superconductor has a critical temperature Tc and critical magnetic field Hc. Now high magnetic field superconductors can operate near the critical magnetic field. It's a type 2 superconductors, making it challenging to maintain superconductivity in extreme strong magnetic fields. So material brittleness, especially in high temperature superconductors like HTS, YBSO, yttrium bismuth copper oxide, and BCSSO, okay, are brittle, okay, brittle and difficult to handle or fabricate into wires and cables. Their fragility makes it challenging to integrate them into large-scale devices that require flexibility and durability. So challenges in high magnetic field superconductors, which cause fabrication and complexity. So these materials are processed used to create high magnetic field superconductors are often expensive. So fabricating these superconductors into practical large-scale devices such as coils for MRI machines or future fusion reactors requires complex, precise methods which increase the cost and time required for production. So cooling requirements where it needs to be cooled at very low temperatures to maintain their superconducting state. And high temperature superconductors still require cooling, often with liquid nitrogen or the other cryogenic fuels, which cryo is nothing but meaning of ice or very cool liquids. But the cooling demands for low temperature superconductors can be even more stringent, require liquid helium. So these cooling requirements are a significant operational cost and logistical challenge, especially in large scale applications. Next, we see the magnetic field induced damage. So while tied to superconductors can withstand high magnetic field, they cannot immune to damage. They are not immune to damage. So excessive magnetic field or the presence of current induced heating can still degrade the superconductive properties over time. So in conclusion, we say that we have a summary right now. We have the high magnetic field superconductors are essential materials in advanced scientific and industrial applications that require the generation and manipulation of strong magnetic fields. These superconductors, partially type 2, let's say, can operate in environments with strong magnetic fields, we say, because of their high superconductive due to vortex formations. In maintaining the superconductive properties, because vortex states and flux spinning. So HTS, the high temperature superconductors, are making significant strides in providing superconductivity at high temperatures, though they still face challenges in terms of material bitness and cost. Importance is in modern technology where superconductors that can withstand high magnetic fields are critical to technologies such as MRI machines, particle accelerators, and magnetic levitation trains and fusion reactors. Their ability to carry current without loss and generate powerful magnetic fields makes them indispensable in a wide range of research and medical applications. So ongoing research and development, we see that there's ongoing research aimed at improving the critical temperature and critical magnetic field of superconducting materials. Innovation in material science, fabrication techniques, and flux spinning are helping to overcome these existing challenges. So in future outlook, we say that magnetic field superconductors holds exciting potential, particularly in the fields like quantum computing, space technology, and energy transmission. So continued advancements could lead to the development of room temperature superconductors, which would revolutionize not only energy systems, but also high-speed transportation and advanced computing as well. So while challenges remain, the importance of high magnetic field superconductors in modern technology can't be overstated. So with ongoing research and breakthrough, these materials will likely play an even greater role in shaping the future of energy, transportation, and scientific exploration. Their unique properties have the potential to lead to innovative solutions for some of the most pressing challenges in energy efficiency, transportation, and healthcare. Thank you.